Hello everyone, and this is Le Chatelier's principle, specifically graphs. So we're going to have a look at some of the ideas about graphing that we learned yesterday. You might want to review those before we start. We'll incorporate them into today's lesson. So here is our first equilibrium. When we're working in graphs, we want to be paying attention to both the equilibrium equation and the graph itself. Don't worry about this particular unit. This is just going to be our concentration. Sometimes when you pull things off the internet, it's not exactly what you want. All right, so the first part of the question is we're going to try to predict what happened at the 20-second mark. Here we go right here. So as you can see at the 20-second mark, the blue line gradually went down, the black line gradually went up, the red line spiked, and then gradually went down. So we had a spike, a single spike. So what we want to figure out is what happened. So is it a C, T, or V, a concentration, temperature, or volume change? And then we want to figure out what happened to the concentration, temperature, or volume. And then we also want to figure out which way it shifted. Let's work it out. So if we have a look at a single spike is a concentration change, and particularly we're looking at CO. So our answer would say that we increased the concentration of the carbon monoxide. And then in terms of the shift, this is where the equilibrium equation is helpful, because if we increase the concentration of CO, let me just put my equilibrium equation there. If we shift or we increase the CO, the shift should go to the right. If we look at the graph, we should see this reflected. So the CO and the CL2 should go down, which it does. It goes down there, and it goes down there. And the COCl should go up. And again, if I have a look at the COCl, it does go up. So we're going to say that the concentration of CO increased, and then there was a shift to the right. Here's our next example. Same thing as before. We've got our same equilibrium, same graph. This time we're looking at what happened at the 33-second mark. So in around here. So again, we're just having a look at the shape of the graph at this section and trying to determine, again, what type of change was it? That was a terrible color to choose. What type of change was it? What specifically happened to that thing? And which way did it shift? So for this section of the graph, we can see that all of the area here, there's no spiking of any sort. So no spikes equals a temperature change. So there's one other piece of the puzzle I'm going to give you. Normally you would be given this. I'm going to tell you that this is an exothermic reaction, and that way we can work out what happened. If it's exothermic, the first thing we would do we would put the energy as either a reactant or a product. If it's exothermic, it becomes a product. So what we're looking at here is a change in temperature. What we want to do is be specific. What type of temperature change occurred? So this time we're going to use the graph first, and then we'll go back to the equilibrium equation. So if we have a look, we can see that the red and the blue line, the reactants, are decreasing. If the reactants are decreasing, that means the shift was towards the right. If it shifted to the right, what must have happened to the energy? Did we add energy or remove energy to make it shift to the right? In order for a shift to occur to the right, it must mean that we removed the energy or cooled the container. That's what would make an equilibrium go to the right if it's exothermic. Let's write that down. So we had a decrease in temperature, or we could say it's cooled, because there was a shift to the right. Temperature is always a little bit confusing. All right, next one. We're looking at same equilibrium, same graph, but this time what happened at the 45-second mark. So again, we're looking at that 45-second mark, and we can see that we have just a single spike. So think about what a single spike means. Wrong color again. Single spike means be specific. Tell me the shift. So going back to my spike here, the spike is of the COCl2, And again, it's an upward spike, so we're going to say there was an increase in the concentration of COCl2. And then we're going to consider the shift. And again, we can go back to that equilibrium equation. If we increase COCl2, the reaction is going to shift to the left to try to use it up. We can confirm this by looking at the graph. So you'll notice on the graph, we have an increase in the blue, the Cl2 increased, and we have an increase in the red, CO increased, and we have a decrease in the COCl2. Again, once we add it in, it gets used up, it shifts to the left, and that's why we see that shift on the graph. So shift to the left. All right, the last one's a little bit tricky. The last one we are going to actually graph ourselves. So we are going to continue, where is it? We're going to continue the graph, and we're going to look at if the volume was decreased. So we're going to continue the graph if the volume was decreased. So decrease in volume. Ooh, that's a T. Decrease in volume. So the first thing we want to consider is, remember that C equals N over V. If we decrease in the volume, we're going to have an increase in concentration. This is going to happen for all entities. Let me just find some colors that are going to work for us here. Okay, so the black, we'll do that one first. We're going to have an increased spike for it. The red is going to have an increased spike, and the blue is going to have an increased spike. So we've now done the first part of the puzzle. The second part of the puzzle is the shift. And if I have a decrease in volume, I'm getting a smaller container, less space equals less moles. So let's go back to this equilibrium equation. If I have less space, less moles, which side of the equilibrium has less moles? Well, on the left-hand side, I have a total of 2, and on the right-hand side, I have a total of 1, which means I'm going to shift to the right. So now I'm going to gradually increase the right-hand side while gradually decreasing the left-hand side. So the right-hand side, the COCl, that's the black line. So I'm going to gradually increase it. If I have a look at what increasing looks like, here's a good example. It's going to go up and then flatten out. The red line and the blue line are both decreasing. So if I have a look at what decreasing looks like, this is a good example of decreasing. It slopes down and then flattens out. Same thing with the blue line. And now I've reached equilibrium once again. So you're going to be working on some homework questions for me in the textbook, and then I also have a worksheet with a couple of graphs on it as well. Graphs, again, are tricky, so use the lesson to help you out and see what you can do.